Hello, everyone. Welcome to Lab 1 of ECE 4270 antennas. So in this lab, we're going to talk about measuring radiation pattern of a half a wavelength dipole antenna. Before starting the lab, let's review radiation pattern. In class, we learned about the analytical method of calculating the radiation pattern. In the analytical method, you need to know the current distribution of the antenna. Once you know the current distribution of the antenna, you're going to use magnetic vector potential, and then from magnetic vector potential, you can calculate far field ENH, and then after that, you can have radiation pattern of the antenna. On the other hand, on the simulation part of our course, we're going to be using an electromagnetic simulator. In that part, we're going to use the simulator is actually solving Maxwell's equation numerically. And when you solve that numerically, you can, again, calculate the radiation pattern of the antenna. In this lab, however, we're going to measure the radiation pattern of the antenna using the lab volt antenna training system. Now, let's review lab volt antenna training system. It consists of 5 main components. So the main component, the first component, is this transmitting antenna. As you see, this is a Yagi-Uda antenna. It has 6 elements. It's the first element, second, third, fourth, fifth, and sixth element. This is the active element. This is essentially fed, and the rest of them are passive. They are used to make the radiation pattern of this Yagi-Uda antenna more directive to this side. And this stand that we have for the transmitting antenna is stationary. It does not move. And then this Yagi-Uda antenna is connected with this cable to the RF generator. Now, this RF generator that we have consists of 2 frequency, 1 gigahertz and 10 gigahertz. So this essentially provides the RF signal for us. For example, in some of the lab, we might be measuring at 1 gigahertz, then we turn on the 1 gigahertz oscillator, and in other lab, we might be using 10 gigahertz, then we're going to turn on the 10 gigahertz oscillator. So these are the 2 components that we have on this side. And then on this side, we have the receiving antenna. And in our case, receiving antenna is the antenna under test. For example, this is a half a wavelength dipole antenna that you see here. So this is our receiving antenna or antenna under test. Then you might ask why we are measuring the antenna under test in the receiving mode. And the reason is due to reciprocity for this half a wavelength dipole antenna, it does not matter if I measure it in the transmit mode or receive mode. It's expected to get the same thing due to reciprocity theorem in electromagnetics. So this receiving antenna is going to receive the electromagnetic radiation coming from Yagi-Uda antenna, and this system is going to convert it to voltage for us. And then this received signal will be communicated with the data acquisition interface that we have here. And this data acquisition interface is connected to the last component of this training system, which is the computer in which we have the software. So the software is going to plot the radiation pattern for us, and it has some processing capabilities, for example, calculating the half power beamwidth of the antenna. So before we start, let's review a few important safety considerations. One safety consideration is that when I turn on this system is going to beep to let me know that electromagnetic radiation is happening in the room. So fortunately, the RF signal coming from this generator is not too high. It's actually very small. In 1 gigahertz, we are talking about 2 milliwatt in this case, which is 3 dBm. So, but in any case, it's good practice to not look directly into the antenna when it's transmitting electromagnetic energy. So when I turn this on, you see that the system is beeping to let us know that electromagnetic radiation is happening. So if I want, for example, to adjust the location of this and I need to look directly into the antenna, it's good that it is off. So that's one consideration. The other thing that you need to be very careful when you are using this RF equipment is to have this wristband here. So this is essentially make sure that the system is safe against electrostatic discharge. So when you are working with this type of system, you need to also make sure that you wear the wristband. So now, the other thing to note is that when we are measuring radiation pattern, we might see some fluctuation in the radiation pattern. Part of that could be due to reflection from the walls. So ideally, you want to measure in free space environment when it's just about the transmit antenna and the receive antenna. But if you look at our room right now, for example, if you look at this room, we have this column right here. And if the electromagnetic waves coming from the Yagi-Uda antenna, part of it could be received by the dipole, and part of it could come here, and a percentage of that would reflect back and again would be received by dipole antenna. And this is not ideal for measurement. So ideally, you want to have this measurement system in an anechoic chamber. Now, I'm going to show you one anechoic chamber that we have in the antenna lab. So if you, for example, come to this room, you're going to be seeing that all the walls are covered by pyramidal absorber. So this pyramidal absorber, or radio frequency absorbing material, or RAM, they essentially absorb electromagnetic energy. So these are ideal for normal incidence. So when the electromagnetic waves comes like this, then the reflection is very minimal from this system. So you can assume that you are operating in free space. For our purpose, we're not going to bring that system into this anechoic chamber. But ideally, if you want to perform very accurate measurements, it's good to be in an anechoic chamber. And we have different type of absorber. This is just one particular type of that, which is called pyramidal absorber. Okay, we want to talk about E-plane cut and H-plane cut. To understand E-plane cut and H-plane cut, we're going to first start by the direction of maximum radiation. So if you consider this dipole antenna that we have, right now we mounted it vertically, and the direction of maximum radiation, this is the direction of maximum radiation. So it's going toward the transmit antenna. So that's the direction of maximum radiation. And also we know that the electric field of this dipole antenna is along this direction. So now we're going to make a plane with these two vectors. So that's the direction of maximum radiation. That's the direction of electric field. Therefore, we're going to have a plane consisting of these two vectors. And if I use this plane, that's essentially my E-plane cut. So this is my E-plane cut. And when you go to H-plane cut, so you're still going to consider the direction of maximum radiation in this way. And now your magnetic field H is perpendicular to it. That was E. Therefore, that would be H. So now you're going to make a plane with the direction of maximum radiation and the direction of the magnetic field. So this is becoming your H plane. So again, to summarize, this was my E plane consisting of electric field and the direction of maximum radiation. This is my H plane consisting of direction of maximum radiation and magnetic field. Now, if you, for example, want to measure the radiation pattern in the H plane cut, this antenna under test needs to move in the H plane cut. So essentially, this antenna, if I use a similar antenna, this antenna is going to be moving in the H plane cut like that, which is completely okay using this system, because this system is azimuthally going to rotate that. So essentially, you're moving in the H plane cut. So you're essentially measuring the radiation pattern in this cut. So, and when you want to do that, you need to be careful that the transmitting the antenna that's going to illuminate the receiving antenna is co-polarized with the receiving antenna. So that's going to make a proper H-plane measurements, or to be more accurate, co-pol H-plane in this case. Now, assume that I want to do E-plane measurements. Now, this is my E-plane, as I mentioned. Now, how would you perform such a measurements? This is going to be a problem for you, because if you want to do H-plane measurements, if this is your antenna, the movement should be in this plane. So the antenna should move like that. But then this system doesn't do that for you because this system only can rotate in the azimuth direction, azimuthly, right? So what we do is instead of rotating the antenna like this, we're gonna rotate everything 90 degree. So we're gonna rotate everything 90 degree and then perform the same movement, right? So instead of measuring like that and rotating like this, we're gonna rotate everything 90 degree and perform the same movement. So that becomes our E-plane cut measurement. But remember, when you rotate everything 90 degree, you also need to rotate the transmitting antenna 90 degree to perform E-plane cut, because now when you do that, the polarization becomes horizontal. So that is right now an H-plane measurement setup. If I want to make it E-plane, everything should rotate 90 degree, and I'm going to use the same measurement system. So I'm going to loosen this up a little bit, and I'm going to rotate this 90 degree. And this, I need to do the same thing. I need to use a different mount, but just for the demonstration purposes, I'm just going to do that so that you can see. So assume that this is horizontal like this. So now if it rotates like that, then you can measure your E-plane cut. So that's a trick that we do to perform E-plane cut. Okay, so right now we want to perform the first radiation pattern measurement. So as you see, we have our Vivaldi antenna, our Yagi-Uda antenna fixed here. So this Yagi-Uda antenna right now has horizontal polarization. Sometimes it's very difficult to figure out the polarization of the antenna, but for this type of wire antenna, it's relatively straightforward. So polarization would be along these rods, so they are all horizontal. So you're expecting that electric field is doing this. So essentially we have horizontal polarization. So this has horizontal polarization, and then we mount our dipole antenna like this. And later on, we're going to ask you some question why we mount it like this and so on. So right now, we also make sure that the height of this is relatively the same as that, and they're looking directly to each other. This has already been set. Now, one thing that you need to be careful is that as soon as I start measurement, this dipole antenna is going to rotate. And the axis of rotation is essentially, this is the axis of rotation. So if I use this rod here, this is essentially the axis of my rotation. And the dipole antenna should be along the axis of rotation. Otherwise, the measurement is not going to be accurate. For example, if I take this dipole antenna and I mount it on this rod here, my measurement would be wrong because that would be the axis of rotation, but now your dipole is here. So you need to make sure that the axis of rotation and the dipole is along each other. So that's one thing to keep in mind for accurate measurements. Now, to start the measurements, I'm going to turn on the system and I'm going to ask the software to start the acquisition, because it's going to be difficult to show you measurement and the software. We're going to have a different video for that so that you can also see what's being plotted as we do the measurement. So the first step is to start the RF power. I'm going to start the RF power. So now beeping starts, but nothing is moving yet because the software has not been started yet. As soon as I start this is going to rotate 360, and as it's going to rotate 360, the received signal will be recorded as a function of angle. So now I'm going to go here and I'm going to go to the acquisition menu and then press start. And I want you to keep an eye on the dipole antenna as it rotates. The Yagi-Uda antenna stays stationary. So as you see, it starts rotating. Now we're almost at 360, and it's done. So now that it's done, the system is going to ask us to save the radiation pattern, and then we can save the radiation pattern, and then we can use cursors to look at different parts of the radiation pattern. Okay, so the previous measurement was essentially E-plane cut. So that was this is a very important cut, E-plane, and the other one, H-plane, that we're gonna see. But before going to H-plane, I want to also talk about one other thing in E-plane. So when this antenna dipole antenna that we had rotated like this, that was our E-plane measurements. But now, if I want to be more accurate, that was co-polarized E-plane, because the dipole antenna had the same polarization as the transmitting antenna. So this transmitting antenna was transmitting linearly polarized in this direction, and this dipole antenna was matched to receive linearly polarized wave. But now I want to keep this in E-plane, but then change the polarization of our transmitting antenna to vertically polarized, so that I have polarization mismatch between the receive and transmit. Because I haven't touched my receiving antenna, I'm still measuring E-plane, but it's going to be this time cross-pole E-plane. So to do that, I'm going to rotate this 90 degrees to not hurt the connector. I'm going to loosen it a little bit, and then I'm going to rotate it 90 degrees. Hopefully this is 90 degrees, and I'm gonna tighten this again. Now, in this case, the situation that we have is that this antenna, let me make sure that it's almost 90. Yeah, so this antenna right now is again linearly polarized, but vertically. So this would be the electric field that's coming toward this antenna. But because this electric field is perpendicular to this dipole antenna at any angles, ideally you have to have zero reception at any angle. But that's not the case in practice. You're gonna still receive signal, and then we're gonna call that cross-pole E-plane pattern. So I'm gonna start the measurement, and we're gonna look at the radiation pattern. If everything is correct, it's expected that the x-pole E-plane pattern would be below co-pole adjacent E-plane pattern. So let me start the RF generator. So now I'm gonna go to the software, and I'm gonna go to the acquisition, and I'm gonna start the acquisition. So as you'll see, it is still gonna rotate similar to co-pole E-plane. And at the end, we need to look at the signal and see how cross-pole pattern is compared to co-pole pattern. Something to note here is that here we're gonna have the effect of cable too, because if you look at the cable structure of the receiving antenna, we might pick up signal due to the cable itself, because cable is now almost in parallel with the transmitting antenna. So that's an issue, and that's part of the reason that sometimes cross-pole might be bigger than what expected. Now I'm going to turn off the signal, and then we can take a look at the pattern. Okay, so the last step that we covered was E-plane measurement, but in the cross-pole. So we rotated the transmitting antenna 90 degrees so that the polarization is not matched to the dipole antenna, and then this was moving in the azimuth direction, rotating in the azimuth direction, and that became our cross-pole E-plane. Now, in this step, we want to go to H-plane pattern measurement. So to do the H-plane measurements, we should move this antenna and put it in a different orientation. So for me to do that, let me start. So the first step, we're gonna remove the cables. So this is this cable. Now we don't need this rod anymore because this rod is very appropriate for E-plane measurements when the antenna is placed like that. So I'm just going to remove that, and I'm also just going to remove the dipole antenna from this rod. So what we're going to do right now, what we're going to do would be to use a different rod this time, and that would be this rod here. So now this rod enables me to plug the antenna like this. So now if you look at this structure right now, if this rotates azimuthly, I'm going to be collecting H-plane measurements, and it's going to be co-pol because now this is also vertically polarized, so the polarization is matched. So if it rotates like that, I can measure my H-plane cut in the co-pol. I just need to be careful that, again, when I'm rotating, I'm going to be rotating the antenna properly. So this is the axis of rotation. So the antenna should be aligned with the axis of rotation. Right now it's a little bit offset. So to adjust that, I'm just going to move it a little bit forward. So if I move it a little bit forward, this seems to be better now. So if you look at this axis of rotation and the antenna, they're reasonably close. The axis of rotation and the axis of the antenna would be close. Now, the previous cable probably is too short for this, so I'm just going to use a new cable which is longer. This is going to be connected to here. So I guess this is a little bit loose. So you make sure it's tight, but not too tight. Okay. So, I mean, if we have a tape, probably if we tape this here, that could be a better installment, but we're gonna just keep it like that. So I'm just gonna double check that the axis is along the axis of the dipole, that's okay. And also gonna make sure that these Yagi UDA antenna is properly set up compared to this. It seems to be reasonable. So I can now start collecting, and if you collect like that, this antenna is going to move again azimuthly like that, and that's going to be your H-plane. Note that again, this is co-pol because now this is vertically polarized, and this is also in a start to be vertically polarized. And so let's perform our measurement and see what we're gonna get. So I'm gonna make the RF power on. So it starts beeping to tell us that now it's on and you have electromagnetic radiation. And then I go to acquisition and I'm gonna have a start the measurement process. So as you see, the antenna is essentially at any angle is the same thing, other than the cables that's moving and the room that's not symmetric. and has some reflection due to wall, the antenna itself is very it stays the same. So you're gonna be expecting that you have a pattern that does not have any angular dependency. Okay, now this is done. Okay, so what happened so far is that we measured E-plane, and in particular, our first E-plane measurement was co-pol. Then we measured cross-pol E-plane, and now this setup is for H-plane measurement. Now we're gonna go to the last one, which is cross-pol H-plane, because antenna is gonna be still in its H-plane measurement mode. To get cross-pol H-plane, I need to rotate the transmitting antenna by 90 degrees so that I have my polarization mismatch. So I'm gonna loosen the connector here, and then I'm gonna rotate this 90 degree, and I'm gonna be tighten this again. So this is now 90 degree right now. So this is now our 90 degree. So this is now horizontally polarized. So electric field is moving in this direction. So ideally, this should not create any received signal on the dipole, because the movement of the electrons on the dipole is supposed to be in this direction, but the electric field, which is essentially our force, is in this direction. So ideally, there would be nothing, but then as you see in practice, we're gonna get some cross-pol component, and the level of cross-pol to co-pol is our cross-pol level. So this is now ready for starting the measurements. So let's start the measurement. To start the measurement, again, I'm gonna turn on the power, and I'm gonna go to the software and start the acquisition. If you later on, you're going to look at the pattern that we have here. It's not really ideal. It can be improved, but still it shows very nicely that the cross-pol level is much smaller than the co-pol level. So this is essentially our polarization mismatch that we had in the Friis equation. Okay, let's focus on how the data collection software is going to plot the polar pattern for us. So we are concerned with half a wavelength dipole antenna in this case, and we're going to take a look right now at E-plane cut in the co-pol case. So we're going to be looking at co-pol E-plane. To start, we can go to acquisition and press start acquisition, or just click on that triangle to start our acquisition. So now the acquisition start, and it's you can easily notice that now as the angle change, the received signal doesn't change much. Now at this point it starts changing, it goes to the null, and again it rises. And now pay attention here that it goes to 0 dB and it just stays there for so many angles. That's an indication that your receiver has been saturated. So to avoid that, you need to apply some attenuation to the received signal to be able to take care of that. And in the right column, we have an option to apply attenuation using the software. So we're gonna do that again. So we go to the right column of the software where you see that 0 there. So if you look at the 0 there, you can change that, for example, to 1 dB, 2 dB, 4 dB. For example, if I do the measurement right now, I'm applying 4 dB attenuation. Let's be on the safe side and apply 6 dB attenuation and see what our result will be. So now using this 6 dB attenuation, I'm going to redo the measurement. So we discarded the previous measurement and we're going to start our new
measurement using this. So we're gonna again press start acquisition, and now as you see, we see angular variation when we are collecting. Now we have to go now at this point to the null, so it's approaching the null, and now it rises again. And now compare this situation here with the previous situation where for all the angles you were receiving the same thing, but now clearly you see your the change in the received signal. Now as we expect, this is the donut shape that we would like to see for half a wavelength dipole antenna. And when the measurement is done, on the right column you can see the maximum signal level received and also the half power beamwidth that the system calculate for us. Now we're gonna save this under document 2. We're going to keep document 1 for later on when we are collecting cross pole. So as you see, the maximum signal level is minus 2.56 and half power beamwidth is 85 degrees. So based on the expected half power beamwidth, the theoretical half power beamwidth, it should be 78, but we are at 85 degrees. So it's acceptable. That's a good sign that our measurement seems reasonable. Now, also we don't have many ripples in our measurement, which is another positive sign. Now that we are done, in the next experiment, we're gonna be measuring cross pole E-cut, E-plane. So essentially, I have now need to rotate the transmitting antenna 90 degree to create that polarization mismatch, and I'm gonna perform the same experiment again under polarization mismatch, which would be cross pole E-cut. Okay, in the previous measurement we had our E-plane cut in the co-pol case. Now we've rotated the transmitting antenna by 90 degree. We kept the antenna under test exactly the same. Now we are gonna collect cross pole E-plane cut. And for that, we also keep the 6 dB software attenuation the same. And we're gonna start our measurement. When the measurement is being done, compare the measurement with this polar plot that you see right now, which was for the co-pol. Now we are right at the cross pole, and you can see that the received signal is in fact much smaller than the co-pol signal that we collected earlier. So that's our cross pole measurements. This antenna is linearly polarized, so it's expected that when we rotate the transmitting antenna by 90 degrees, the signal received by this antenna drops significantly. So it's almost done. So our cross pole measurement is done. Now we're gonna save that as E-plane under document 1.ant. So previously we saved that E-plane at document 2. That's going to be our document 1. And if you look at document 1, you see that the maximum signal level is at minus 20 dB, whereas the maximum signal level in the co-pol case was in the order of minus 2.5 dB. And I'm not going to interpret the half power beamwidth of the cross pole because the level of the signal is so small. So in this case, we are about 18 dB from difference between the maximum signal level that we have. So that's going to be our cross pole E-plane for the half a wavelength dipole antenna.
Okay, so we've done our co-pol E-plane and we've also done our cross-pol E-plane as you see on the screen. Now it's time to go to
co-pol H-plane. To do that, we need to set up the antenna in the H-plane data acquisition mode, and also make sure that the polarization of the transmitting antenna is matched so that we can collect co-pol. Now, so we are ready to do that. Just wanted to remind you again that on the right you see two documents, document1.ant, document2.ant. So document 2 was for co-pol, that now we need to collect is H-plane. Now I press the acquisition button and we are now getting the data. So ideally or theoretically, the H-plane of a dipole antenna needs to be like a circle. It's an omnidirectional pattern, so it should be identical. Of course, the antenna itself is completely symmetric in this plane, but remember that we have cable feeding the antenna and other things, the room itself, so we may not have a completely symmetric situation. But as you see, the result is actually very nice. It's like a circle, and you see that in this plane it's actually omnidirectional. This is in contrast to E plane, that we had the donut shape and we were directional. Now if you look at the mouse, it was showing the maximum part of the signal for both cases sometime earlier, and as you see, they're on top of each other. So when you look at the maximum of the signal, they're almost on top of each other, and that's an indication of good measurement. The E plane, the maximum of E plane and maximum of H plane ideally need to have the same MSL, but in this case we have some discrepancy. The MSL is minus 2.56 for E plane, and it's about minus 1.6 in the H plane. So they're about less than 1 dB apart, which is completely fine for this measurement system. But that's a very important thing when you are measuring a pattern. Always check for the peak of the E plane and H plane. And you need to make sure that you're checking this. And in this case, as long as we are less than 2 dB for this measurement system, we are happy with our result. So now we have co-pol of H plane, and the next one that we want to show you would be the cross pole of H plane. Okay, now we have measured co-pol E plane, then cross-pol E plane, then co-pol H plane. Now we need to start cross-pol H plane. So, the co-pol H plane was completely circular, as you see here. So that's an indication of omnidirectional. Now we need to check how it cross-pol would look like. This is now the highlighted one is co-pol E plane. Again, back to co-pol H plane, so that you can see what we already got. So in one plane, our dipole antenna is directional. In the other plane, it's omnidirectional, almost no angular dependency in the H plane. And this is somehow expected, because if you cut the antenna in the H plane from the dipole antenna, you essentially see a point, only a point. So, and from every direction, it will look the same. Now, to do cross pole H plane, we kept the antenna under test as it was earlier in the co-pol H plane, but now we rotated the transmitting antenna by 90 degrees. So this rotation is essentially to create 90-degree polarization mismatch. So ideally, you say you're not supposed to receive anything, but because we also dealing with other things like cables and so on, you're gonna still have cross pole signal. Now let's start our acquisition. So we can go to the menu and press acquisition, and now we are starting our acquisition. And as you see, in fact, the cross pole level is not as low as we might have expected. So this is one question that I will have for you to justify this based on the measurement configuration. So as you see, our cross-pole level in particular is higher than the cross-pole of E-plane, and so when we look at the maximum signal level, we can actually see exactly what is the maximum signal level. But in any case, you see that your cross-pole level is anyway smaller than the co-pole level. So if you compare, now it is complete. This is the cross-pole H-plane that we obtain using this system. If you compare it with co-pole H-plane, definitely it's smaller. But the question is, why it's more, the cross pole level in this case is more than the cross pole level in the E plane, and also would you expect the cross pole to be this much? Now if we look at the maximum signal level, you can compare the maximum signal level. It's minus 12.3 in the cross-pole H-plane, and if you compare it to the co-pole level, which was minus 1.66, so it's almost 11 dB smaller in the case of cross-pole and co-pole H-plane.
Okay, so in this test, we're going to see what's going to happen if we increase the distance between the transmit and receive antenna. So what you're going to see shortly is that I'm gonna perform one measurements like that with this distance between the transmit and receive antenna, and then in the next experiment, I'm going to increase the distance between transmit and receive antenna. Now, I could, for example, make this a little bit farther or make this a little bit farther. But if you notice here, we have two tables here. So if I move the transmit antenna to this side, probably I'm going to place it on a different table, and I could have some problems with vibration on the other table because I will be sitting there. So it's better for mechanical stability that I move the receive antenna a little bit farther. In that case, they're going to be both on the same table, and hopefully the table would be stable during the measurement. So this is one measurement. The second measurement, I take the receiving antenna and I move it a little bit farther, and then we see what's going to happen. Remember that ideally under perfect far field condition, the pattern of the antenna should stay the same. And when I say pattern, that means angular distribution. Of course, when you are measuring the received signal, it's expected to drop based on Friis equation as soon as you increase the distance between the transmit and receive the antenna. But for example, half power beamwidths should stay the same. Lab, we're going to take a look at what's going to happen if we increase the distance between transmit and receive antenna. So to do that, let's start acquisition of an E-plane pattern of a half a wavelength dipole antenna. And then we're going to do the same thing, but this time we're going to increase the distance between transmit and receive antenna. This beep that we have in the background shows that the transmitter is on and the system is ready to record the pattern. So I'm just going to start with the acquisition right now. So if I press start acquisition, it starts plotting the pattern for me. And because this is the E-plane, you expect to see that donut shape. Right here, you see that we have a bit of problem. It seems the system has been saturated because we're going to be recording all maximum value for so many angles. So we need to take care of that later on. So you essentially see the shape, and again here you see that saturation effect. So we need to take that into account. and this is now done. So to take that into account, I'm not going to save that for now. I'm just going to perform another acquisition. To make it correct this time, I'm going to apply a little bit of attenuation using software. So here you see that currently it's at 0, so we're not applying any software attenuation here. So I'm just going to increase it to maybe 4 dB in this case. So let's start again. And now you see, we should see a better pattern. As you see now, we are not saturating, so we see the angular distribution. It's better than the previous case. I mean, we could have tried a bigger attenuation, but for the purpose of this demonstration, I think this is reasonable. So we go to our null, and then we're gonna go again to our maximum and come back to the null. Okay, so that's the E-plane pattern for this antenna. So what I can do, I can just save it under E-plane. So it's actually the pattern that we got is reasonable. As you see, the half power beamwidth theoretically should be 78. In this acquisition, we got about 82.7. So if we want, we could set the maximum signal to 0. And this gives us this pattern. Now the next step would be to increase the distance between transmit and receive antenna, and I'm gonna do that, and we're gonna perform another acquisition. So I'm just gonna a little bit increase the distance between these two, and let's see what's gonna be the effect. Okay, now the distance has been increased a little bit, and we're gonna perform another acquisition. Remember that I kept the same software attenuation as 4 dB here. So we're gonna press start, and remember that in this new acquisition I have not rotated the pattern yet, but later on I can rotate it to better compare it to the previous acquisition. So let's start our acquisition. So this is for the new antenna. So what we expect is that when we increase the distance, the received signal should be smaller according to Friis equation. But then the overall shape of the radiation pattern should stay the same, because the shape of the radiation pattern should not depend ideally on the distance if you go far enough. If you don't go far enough, then with the change of distance, you're gonna have different distributions of electromagnetic fields. So now this is going to be my second acquisition. I'm going to save it under a new document. Again, it's E-plane. So I record that E-plane. And to be consistent with the previous case, I could also rotate it so that the maximum signal level is at 0. So now you see that, and this is the two pattern that we collected. Now what I want you to pay attention here is that this is the first acquisition that we had. It was at a smaller distance. Now if you consider this one and compare it with the new acquisition, which was at a larger distance, you see that when you increase the distance between transmit and receive antenna, your signal has been dropped. So now if we compare the two signal level, in the first case, the smaller distance, the maximum signal level is minus 0.82, and in the second case the maximum signal level is minus 2.42. And the half power beamwidths estimated by both of them are very close. One of them is 82.7 degrees for the smaller distance, and the other one is 80.34, and ideally it should be 78 degrees if you are far enough so that the far field condition is completely satisfied. The other thing that you might notice here is that we have more ripples in the case that we have a smaller distance. One of the reasons could be, sorry, in the case that it's a larger distance between the two antennas. One of the reasons, just only one of them, is that when you increase the distance a little bit, then what's going to happen is that the surrounding, for example, the space between the two antennas would be more visible to the antenna. So you could have more reflections from the table that we mounted the two antennas. And also other reasons. So this could be a potential reason in this case. Now, so we established this, and you could now investigate based on this number that I gave you, that how what is the difference between distance between these two experiments. In this experiment, we're gonna perform two different types of acquisition. The first acquisition would be simply the E-plane cut of a half a wavelength dipole antenna. So this would be the system that we are using. The second acquisition, I'm gonna place my hand here and I'm gonna perform another acquisition. So we're gonna see what would be the effect if I perturb the distance between, if I essentially have an object between the antenna under test and transmitting antenna. So I'm going to place my hand like that, and I'm going to perform another acquisition, and then we can compare these two acquisitions.
Okay, so the purpose here is to study how the placing of my hand beside the transmitting and between the transmitting and receiving antenna will play a role. So to do that, let's start with measuring E cut of a half a wavelength dipole antenna when there is nothing between them. The reason that I'm repeating this measurement is that something has changed and it's not at the same time as previous measurement, so it's good to do another measurement to be consistent. So let's do that without having my hand. So similar to previous cases, we've had this 4 dB software attenuation. On the right you can see that. Then we now go to acquisition and start our acquisition. So as I mentioned, this is the E-plane cut. It's co-pol of half a wavelength dipole antenna. The only thing between the transmit and receive antenna is free space. We don't have anything else. So we still see a little bit of ripples in the radiation pattern because we've set the software attenuation on the right column to 4 dB. You see that we don't go to the maximum, so we don't have the saturation. Here we go to the null, then we go back again, and we're approaching the peak. So when this is done, it's a good practice to check what kind of half power beamwidths we got. So now the measurement is done. So you can see that our half power beamwidth is about 75.5, which makes sense. The theoretical level is 78. Now you can of course choose to rotate the pattern in such a way to have its maximum at 0 if you'd like to do that, or you can keep it like that depending on what you prefer.
Okay, right now in the screen we have the co-pol E-plane pattern of a half a wavelength dipole antenna when there is nothing between the transmit antenna
and the AUT. Now, as we mentioned, I'm placing my hand between the transmit and receive antenna, and we are collecting. So what you are seeing right now is, uh, in fact, includes the effect of my hand between the transmit and receive antenna. Now, what I would like you to consider is to analyze why we see this structure, in particular, why the level of the signal is lower, and also when we get to the null, for example, we just crossed the null of the original E-plane cut, why it's a little bit higher in now in this new data collection. So our data collection is almost done. Now we can compare these two cases, and then we could consider, for example, the maximum signal level. For example, right now the original E-plane was under document 1.ant. Now I'm storing this new one under document 2.ant. And if you look at the maximum signal level, the maximum signal level has dropped from about -2 dB to about -7 dB. So it's about 5 dB smaller in this new case. So that should be due to the effect of my hand that I place between the transmit and receive antenna. So in this experiment, we want to study what's going to happen if the axis of the dipole is not along the axis of rotation. So if you want to check, for example, this case, you could simply use this, and you can somehow check if the axis of your dipole is along the axis of rotation. So in this case, it's not perfect, but it's acceptable to us. So if I have it like that, this is the axis of rotation, which is almost on top of the axis of antenna. Now, to check what's going to happen if the axis of dipole is not on top of the axis of rotation, I'm gonna move this dipole to a different location. So I'm just gonna take this dipole, and I'm gonna loosen this, and I'm gonna place it here. So now this is gonna be my new setup. Of course, you realize that, I mean, the 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 axis of dipole is now along this line, whereas this is the axis of rotation. So to demonstrate it better, let me bring another rod. So this rod shows the axis of rotation. We are rotating around that, but this is now the axis of the antenna. So, but I mean, this is not the only thing that we've changed, because as soon as we change it, the structure of the cable will change too. So, but it's mainly about the axis of the dipole. Now we're going to perform another acquisition and check what's going to happen when this is the case. So what you see on the screen is an E-plane cut co-pol that we already performed. Uh, so in this case, we have a half power beamwidth of about 80 degrees using 5 dB attenuation that I applied using software. So you can also compare this measurement with the previous co-pol E-plane to understand the uncertainty associated with these measurements. Now we're gonna collect another one for the case that the axes are not on top of each other. Now, as you see, this new measurements that we are performing right now is associated with the case that dipole axis is not on top of the rotation axis. So as you see, we lose that symmetry that we had in the original pattern. So, and that demonstrates the importance of making sure that the axis is correct. So you essentially want to measure the same antenna as you are rotating.
and you need to be careful about how you place your antenna on the mount. Now our measurement is essentially done. You can compare these two sets of measurements and see how they differ.